Welcome to this course on Theory of Plasticity for Engineers, Concepts and Applications. We are dealing with Module 2, where we are looking at applications of plasticity theories in metals, reinforced concrete and composites. In this lecture, we are going to understand how elastic plastic analysis can be applied to understanding behavior of composite materials. The outline of the lecture is as follows. We first try to understand what are composite materials. We will look at prevailing failure criteria that are there for understanding failure of composites. We will look at effective stress, strain and yield criteria and flow rule, how they are defined for metal matrix composites, and how effective constitutive relations can be defined for composite materials. And in a damaged composite system, how to determine the stresses and how the damage evolves in a composite system will also be understood in this lecture. So, to start with, what are composite materials? A composite is an engineered material that combines two or more constituents to make a material with improved or enhanced properties over either of the individual constituents. Essentially, in case of fiber reinforced composites, you have fiber and matrix together, which are combined in certain proportions to get enhanced properties. So, in case of laminated composite, essentially it is a stacking of several layers or of lamina to form the laminate, and an individual lamina consists of fibers which are embedded inside a matrix, and it is an engineered material, thereby the enhanced properties are achieved from the individual constituents. In this picture, you can see a fiber reinforced composite. On the right side, you can see different types of fibers like carbon fibers or O1 glass fibers that are shown in the figure. Now, in a laminated composite material, essentially has fiber plus a matrix to form a lamina or a composite material, where the lamina is arranged in a unidirectional fibers. So, lamina can have fibers running in different directions as shown here. Depending upon, as you can see here, you can have the fibers oriented in different directions. You can have a stacking. This is essentially a stacking of several layers of lamina, and this results in a laminate which makes up the thickness. An individual lamina consists of fiber and a matrix. Fiber properties and volume fraction are given by EF and XF, and matrix property is denoted by EM and XM. This two come together to form a composite material whose properties are given by EC and XC. So, we have the direction 1, which is aligned along the fiber, 2 is the direction perpendicular to the fiber, and 3 is the transverse direction. The properties of the lamina are going to lie in between the properties of the matrix and fiber, and depending upon the orientation of the fiber, the properties are going to change. So, the fibers can be oriented from 0 degree to 90 degree. So, you have when it is a 0 degree and when the fibers are oriented in the direction of the loading, then you call them as unidirectional fibers, and if the fibers are oriented at 0-90, then you call it as a cross ply. If they are oriented at an angle with respect to the direction of loading, you call them as angle ply. You also have where lamina can also contain O1 fibers, where you have the fibers running in fill direction, or in the perpendicular to the fill direction is the wrap direction. And this stacking of the laminae results in several types of composites as cross-ply and angle-ply laminates, or symmetric or anti-symmetric laminates, or unsymmetric laminates. So, fiber reinforced composite materials, there are different types of composites. One is unidirectional fiber reinforced lamina is shown here, and then you can have bidirectional fiber reinforced lamina is shown in figure C, and where the fiber families are aligned at angles theta and theta dash. In case of unidirectional, the fiber is aligned at an angle theta with respect to direction of loading. Different types of composites can be short fiber composites, long fiber composites, composites where we have layered reinforcement. There can be particulate composites like concrete. Can be functionally graded composites where the volume fraction and properties are graded to suit certain functional requirements. You also have polycrystalline materials with varying grain boundary sizes, which can constitute a fiber reinforced composite material. So, the mechanical behavior of composites: composite materials are non-homogeneous or inhomogeneous or heterogeneous in nature. The properties depends upon what is the volume fraction of individual constituents that are present inside that body of the composite. Composite materials can be treated as either orthotropic or non-isotropic, or in general anisotropic. And essentially, when the material properties are different in different directions, the composite is treated as anisotropic. If the material properties are different in 3 or 2 mutually perpendicular directions, then we can treat them as orthotropic with different material planes of symmetry. An isotropic material has same properties in different directions. So, when we deal with understanding the behavior of composites, because the composites are inherently heterogeneous in nature, they are conveniently studied in 2 aspects, either at a macro mechanical or structural level as is shown here, or at a constituent level, or at a micro mechanic, or at a macro mechanics level. So, in case of macro mechanics, it is the study of behavior of composites, wherein the material is assumed to be homogeneous, and the effects of the constituent materials are detected only as averaged apparent macroscopic properties of that composite material. So, essentially the at a structural level or at a laminate level deals with macro mechanics, and micro mechanics deals with wherein the interaction of the constituent materials is dealt with at a microscopic scale, and to determine what are the effects of individual constituents on the properties of the composite material. Now, composites are classified depending upon the choice of the matrix and depending on the choice of the reinforcement material as metal matrix composites, ceramic matrix composites, or polymer matrix composites, and depending upon the type of the reinforcement as metal reinforcement, ceramic reinforcement, or polymer reinforcement, or elemental reinforcement. And so, the 3 broad classifications include metal matrix composites, ceramic matrix composites, and polymer matrix composites, and specific combination of the matrix and the reinforcement finds different applications as is indicated in this particular table. Now, understanding failure in composites is important to design composites. So, there are different failure modes in composites. So, when we take a 3-dimensional view of composites, you can have interlaminar delamination or cracking as is shown here in this schematic figure, or there can be a translaminar crack that is going through the thickness of that particular layer between the layers, and there can be interlaminar crack. And essentially, when we take mechanical representative volume of composite, the different failure modes include matrix rupture, longitudinal matrix cracking, which is there is a crack that is going all along the fiber. In some cases there can be transverse matrix cracking, where the crack is going in a transverse direction. There can be fiber matrix debonding, or there can be fiber rupture or fiber breakage. Fiber can get pulled out of the matrix, called fiber pullout, and there can be fiber that is bridging between cracked matrix. So, there can be fiber bridging that may be happening. So, these are different failure modes that are commonly seen in case of composites. So, there are some failure criteria that will tell us when does onset of failure happen in the case of composites. So, the onset of failure happens can be defined by what is called as a maximum stress failure criterion. The onset of failure happens when the state of stress along principal material axis exceeds the corresponding strength in that direction. So, for tensile type of failure, if sigma 1 is greater than xt or sigma 2 is greater than yt, then we say that there is a tensile failure. And for compressive failure, if sigma 1 is greater than xc or sigma 2 is greater than yc, then it is called as a compressive failure. And for shear failure, tau 1 2 is greater than s is called as a shear failure, where sigma 1, sigma 2 and tau 1 2 are the stresses that are acting on a unidirectional composite along the principal material axis, and xt, yt, xc, yc denote the allowable or permissible tensile and compressive strength values in the respective material directions, and capital S is the allowable shear strength. So, when this is satisfied, then we say that there is onset of failure based on maximum stress criteria. Now, there can also be a criteria based on maximum strain failure criteria. According to this criteria, the onset of failure occurs in a composite when at least one of the strain components along the principal material axis exceeds the corresponding strain in that particular direction. So, for tensile and shear failure, we are having epsilon 1 is greater than x epsilon t, or epsilon 2 is greater than y epsilon t, or gamma 1 2 is greater than s of epsilon. For compressive failure, we have epsilon 1 is greater than x epsilon c, or epsilon 2 is greater than y epsilon c, where x epsilon t is the maximum tensile normal strain in one direction, that is the direction along the fiber, and x epsilon c is the maximum compressive normal strain in the one direction. Similarly, y epsilon t is the maximum tensile normal strain in two direction, and y epsilon c is the maximum compression normal strain in the two direction. S epsilon is the maximum shear strain in 1 and 2 coordinates. One can define x epsilon t as xt by E1 and x epsilon c as xc by E1, y epsilon t as yt by E2 and y epsilon c as yc by E2, and s epsilon as s by G12, where xt, xc, yt, yc and s are the tensile strengths and allowable tensile and compressive strengths in respective material directions, and S is the allowable shear strength. E1 and E2 are the modulus values in the 1 and 2 directions, and G12 is the shear modulus in the 1-2 direction. Now, the next failure criteria, the Tsai-Hill failure criteria, that is used for defining failure in composites. According to this failure criteria, we have the onset of failure happens when sigma 1 square by x square minus sigma 1 sigma 2 by x square plus sigma 2 square by y square plus tau 1 2 square by s square is equal to 1, where x is the allowable strength of the laminate in the longitudinal direction of the ply in the longitudinal direction, and y is the allowable strength of the ply in the transverse direction, and S is the allowable in plane shear strength of the ply between the longitudinal and transverse direction. There is a considerable interaction that exists between the failure strengths x, y and S. As per this criteria, the variation of the strength with angle of lamina of the fiber orientation is very smooth and is adopted. So, a generalized quadratic failure model for composites which are under plane stress of strain can be written according to the Saifu failure criteria, and this can be represented as F1 sigma 1 plus F2 sigma 2 plus F11 sigma 1 square plus F22 sigma 2 square plus F66 tau 1 2 square plus 2 F12 sigma 1 sigma 2 is less than 1, where Fi and Fij are experimentally determined the strength coefficients. So, for instance, F1 is denoted as 1 by xt minus 1 by xc, and F11 is denoted as 1 by xt times xc, and F2 is denoted as 1 by yt minus 1 by yc, and F22 is denoted as 1 by yt times yc, and F66 is denoted as is equal to 1 by s square, where xt, sc, xc, yt, yc and s are the respective strength values in tension and compression, and s is the shear strength value. The interaction coefficient F12 is typically obtained from a biaxial loading test in the above expression. Now, there are different macroscopic failure criteria that are defined for composites that are very useful to predict onset of failure in the case of composite. Two most popular failure criteria are, number one is the Hessian failure criteria and number two is the Puck's failure criteria. The Hessian failure criteria involves more than one stress component to evaluate the different modes of failure in composite, indicating that the stresses in a composite system interact with each other to cause the onset of failure. And the criteria involves 4 failure modes are defined as per the Hessian criteria, and certain failure indices are related to fiber and matrix failure. The criteria assumes a quadratic interaction between the tractions acting on a plane of failure by calculating the angle of fracture for an given element. So, essentially for a tensile fiber failure mode, sigma 11 is greater than or equal to 0. So, we can say for the Hessian, for any sigma 11 greater than or equal to 0, according to Hessian failure criteria for tensile fiber mode type of failure, sigma 11 by xt whole square plus sigma 12 square plus sigma 13 square by S12 whole square must be equal to either greater than or equal to 1 for failure to occur, and if this quantity is less than 1, then there is no failure in the tensile fiber mode. For compressive fiber mode type of failure, when sigma 11 is less than 0, sigma 11 by xc whole square must be greater than or equal to 1 for onset of failure, and if it is less than 1, then there is no failure. So, in the above equation, sigma ij represents the stress components, and the tensile and compressive allowable strengths for lamina are denoted by subscripts T and C respectively. So, in the above expression, xt and yt and zt denote the tensile strengths in the 3 respective material directions. Xc, Yc and Zc denote the allowable compressive strengths in the 3 respective material directions. So, according to Hessian criteria, there can also be a tensile matrix mode type of failure, and matrix mode failure will happen when sigma 22 plus sigma 33 is greater than 0. So, for this state of stress, the tensile matrix mode type of failure is represented as sigma 22 plus sigma 33 whole square by yt square plus sigma 23 square minus sigma 22 times sigma 33 by s23 square plus sigma 12 square plus sigma 13 square by s12 square must be greater than equal to 1 for onset of failure in tensile matrix mode when sigma 22 plus sigma 33 is greater than 0. If this value is less than 1, then there is no failure in tension in the matrix. So, for compressive type of failure in matrix, for compression matrix mode failure, when sigma 22 plus sigma 33 is less than 0, the above expression now gets modified as yc by 2 s23 whole square minus 1 times sigma 22 plus sigma 33 by yc plus sigma 22 plus sigma 33 whole square by 4 s23 square plus sigma 23 square minus sigma 22 times sigma 33 by s23 square plus sigma 12 square plus sigma 13 square by s12 square must be greater than equal to 1 for onset of failure in compression matrix mode, and if this value is less than 1, then there is no failure. For fiber matrix shear out type of failure, the onset of failure will take place when sigma 11 by xc whole square plus sigma 12 by s12 whole square plus sigma 13 by s13 whole square must be greater than equal to 1 for failure, and when this value is less than 1, there is no failure. So, in the above expression, S12, S13 and S23 denote allowable values of shear strength values in respective principal material directions, and XC, YC, ZC, XT, YT, ZT denote the compressive strength and tensile strength values in the respective material directions. Sigma ij denotes the stress components, and the tensile and compressive strength allowable values are denoted by suffix T and C. So, the Hashin failure criteria essentially has 3 criteria for matrix failure, and it has 2 criteria for fiber failure in either tension or compression mode, and in matrix we have tension, compression and fiber matrix shear out. The second type of macroscopic failure criteria that is commonly adopted for composites is called as the Puck's failure criteria. So, fiber reinforced composites show brittle fracture behavior and a sudden transverse direction failure. The fiber failure and interfiber failure in a unidirectional composite are considered. So, especially the interfiber failure is an added mode of failure that has been considered in the Puck's failure criteria, that accounts for what is the strains and stresses in the transverse direction when it is loaded in the linear direction. So, the fiber failure gives 2 physical modes and interfiber failure gives 3 different physical modes of failure according to this criteria. So, totally the Puck's failure criteria has 5 different modes of failure defined in this criteria. So, according to the Puck's failure criteria, we have a dominant tension when the stress parallel or along the fiber will result in the breakage of fiber. So, we have fiber fracture. There could be fiber fracture due to shear, and the fiber can also fail due to dominant compression. So, you have fiber micro buckling and fiber kinking due to buckling that happen due to shear. So, where sigma parallel is indicating the that the stress state is along the fiber, that may result in fiber failure caused by sigma parallel because of either dominant tension or dominant compression. So, in dominant tension we have fiber fracture and fiber fracture due to shear. In dominant compression we have fiber micro buckling and fiber buckling due to shear or due to kinking. So, Puck's criteria, the fiber failure can be represented in this fashion. The fiber failure due to compression and tension are presented here. When we look at fiber failure due to tension, we can write as 1 by R parallel in tension to times sigma 1 minus nu parallel and perpendicular. So, these notations are used to indicate that whether it is parallel direction, and this is parallel to the fiber direction, and this perpendicular symbol indicates perpendicular to the fiber direction. So, essentially when we look at nu perpendicular parallel is essentially indicating the major Poisson's ratio of unidirectional laminate, and nu perpendicular parallel F indicates major Poisson's ratio of the fiber. So, we have a nu perpendicular parallel indicating major Poisson's ratio of unidirectional laminate, and nu perpendicular parallel F indicates major Poisson ratio of the fiber, and E parallel indicates longitudinal modulus of lamina parallel to the fiber. E parallel F indicates longitudinal modulus of the fiber, and sigma 1 is the longitudinal stress in the fiber, sigma 2 and sigma 3 are the transverse stresses to the fiber direction. M sigma F is the magnification factor for transverse stresses in the fiber. So, essentially we have R parallel TC indicates the fiber strength value parallel to the fiber in tension or in compression. So, when we have R parallel T, it indicates fiber strength in parallel to the fiber, and R parallel C indicates fiber parallel strength in compression. So, the Puck's failure criteria for onset of failure in fiber due to tension is when this factor is greater than or equal to 1, then we say there is onset of failure. So, in compression, when this factor times sigma 2 plus sigma 3 is greater than 1, then we say there is onset of failure in fiber due to compression. Now, matrix failure can be defined in the following forms, which is denoted as interfiber fracture or IFF. Interfiber fracture can be because of transverse tension in a and then it can be because of transverse compression, or it can be because of transverse shear and longitudinal shear, all defined with respect to the fiber. So, if this transverse tension is perpendicular to the fiber, transverse compression is also perpendicular to the fiber, transverse shear is indicated here, which is perpendicular to the fiber in the shear direction, and then we also have longitudinal shear, which is both in perpendicular and parallel direction. So, we have 4 criteria for the interfiber failure or the matrix failure. So, based on the angle of fracture plane, the 3 modes of interfiber failure are shown below. So, we have the strength value in the perpendicular direction in tension, then we have strength value in perpendicular direction in compression, then we have the strength value in perpendicular and parallel direction, which is denoting the shear strength. So, on the horizontal axis we are having sigma 2, the normal strength value, the tau 1 2 is the shear stress value. This is a plot between the normal stress and the shear stress. The failure curve or the failure envelope is indicated here. There are 3 regions which corresponds to 3 modes of failure for interfiber failure. One is called mode A, which corresponds to a tensile stress on plane perpendicular to the fiber and in plane shear stress. And there is a mode B, which is denoted by this green line, which is the small compressive stress on plane perpendicular to the fiber direction, and small in plane shear stress. And the last one is the mode C, which is the large compressive stress on the plane perpendicular to the fiber direction and small in plane shear stress. So, so in the mode B and mode C, the in plane shear stress is small, and in mode C the extent of compressive stress on plane perpendicular to the fiber direction is very large. In mode B, the extent of compressive stress on plane perpendicular to the fiber direction is very small. So, this is like low compression mode B, and mode C is like high compression and for small in plane shear values, whereas mode A is a purely tensile mode perpendicular to the fiber, and it has some amount of in plane shear stress. So, the three interfiber failure criteria are written here. So, where we have based on the plane that we are considering, we can define P perpendicular perpendicular, P perpendicular parallel, indicating the slopes of the plane on which the stresses are considered, and the fracture envelope. So, slopes of the stress plane and fracture envelope, and based on what is the intensity of the shear stress of a unidirectional layer in the elastic symmetric direction, and Fw is a weakening factor due to the degradation influence of the high value of sigma 1, and we are going to have R perpendicular A, which indicates fracture resistance of action plane against its surface due to transverse shear stressing. So, we define an action plane whose slopes are defined using P parallel parallel or P perpendicular perpendicular and P perpendicular parallel, and sigma 1d indicates the stress value for a linear degradation. So, essentially we are going to have mode A, mode B and mode C defined, and S21 indicates the shear strength of the UD layer transverse and parallel to the fiber direction. So, interfiber failure, we can have three modes, mode A, mode B and mode C, depending on what is the extent of the compressive stress on plane perpendicular to the fiber and for a given amount of in plane shear stress. And we can also have in mode A the tensile stress on plane perpendicular to the fiber and some amount of in plane shear stress. So, these three interfiber modes, mode A, mode B and mode C, are described here, which tell us when does onset of failure take place either in mode A, mode B or in mode C. Now, we can also define a damage in case of composites. Apart from considering the macroscopic failure criteria, one can define a damage model for composites to define onset of failure or damage in composites. So, in a damaged composite, the stress strain relationship can be defined through a damaged elasticity tensor, which is denoted as CD. So, the stress state is related to the strain, the stress tensor is related to strain tensor through the damaged elastic tensor, which is denoted as CD, and which can be defined via a scalar damage model like this, where CD is equal to 1 minus di times C, where di takes the value of either d1, d2 or d3, where C represents the undamaged elastic tensor, di, where I can be taking values 1, 2 or 3, represent either fiber breakage, matrix cracking or fiber matrix interface debonding respectively. So, when di is d1, then it is corresponding to fiber breakage, and if it is d2, then it is corresponding to matrix cracking, and if it is d3, then it is corresponding to fiber matrix interface. So, the constitutive matrix for the undamaged elasticity tensor can be written for plane stress type of a situation as given here, 1 minus nu 1 2 times nu 2 1, where nu12 and nu21 are the Poisson's ratio defined in 1,2 or 2,1 direction. E1 and E2 are the modulus of elasticity in E1 and E2 direction. So, is C is equal to 1 minus nu12 times nu21 E1, nu21 E1 0, nu12 E2 0, 0 0 1 minus nu12 nu21 times G12, where G12 is the shear modulus. Now, the damaged elasticity tensor CD is written in terms of C as 1 minus di times C, which can be rewritten as M times C times M transpose, where M is a matrix representing the extent of damage, which can be written as M is equal to under root of 1 minus d1 0 0, 0 under root of 1 minus d2 times 0, 0 0 under root of 1 minus d3. Now, so when we simplify and when we write CD is equal to M times C times M transpose, it reduces to the form as given in equation 4, where E1 and E2 are the longitudinal and transverse moduli, nu12 and nu21 are the Poisson's ratio, and G12 is the shear modulus, and all the damage variables, whether it is D1, D2 and D3, the value will go from 0 to 1, and a 0 state corresponds to no damage and a state of 1 corresponds to a fully damaged state. And essentially the scalar damage variable D1 operates on E1, D2 operates on E2 and D3 operates on G12. And combination of D1 and D2 operate on E1 and D1 and D2 operate on E2 depending upon how we want to reduce the elastic constitutive matrix using the scalar damage variables D1, D2 and D3. Now, intralaminar damage model D1 now can be defined in terms of D1T and D1C, and D1T and D1C denote the damage variables for fiber tension and fiber compression, and D2T and D2C denote the matrix tension and matrix compression. So, essentially for fiber failure we can have epsilon 11 greater than 0 in tension, and in compression onset of failure can happen when epsilon 11 is less than 0 and D1 is denoted by D1C. And in matrix failure, when epsilon 22 plus epsilon 33 is greater than 0, there is a tensile failure, and the extent of failure is denoted by D2 and is represented by D2T. And when the failure is in compression, then epsilon 22 plus epsilon 33 is less than 0 and D2 is denoted as D2C. And D1 plus D2 plus D3 is equal to 1. So, therefore, D3 becomes 1 minus D1 minus D2, which can be further simplified as 1 minus of 1 minus D1T times 1 minus of D1C times 1 minus D2T times 1 minus D2C. So, strain is more continuous and smoother during the damage evolution compared to the stress. So, such a definition is used for intralaminar damage model. Now, the intralaminar damage model, the failure criteria for fiber and matrix under tensile and compressive stress states are: for tensile failure, when epsilon 11 is greater than 0, we can write an epsilon 1 equivalent, and this epsilon 1 equivalent should be greater than or equal to epsilon 1 T naught, which are the critical strength values in critical strain values in tension. And for fiber compressive failure, when epsilon 11 is less than 0, epsilon 1 equivalent must be greater than or equal to epsilon 1 C naught, which is the critical value in compression of strain. So, maximum tensile failure will happen when epsilon 22 plus epsilon 33 is greater than 0. In this case, the epsilon 2 equivalent must be greater than or equal to epsilon 2 T naught for tensile type of failure in the matrix, and the matrix compression failure will happen when epsilon 22 plus epsilon 33 is less than 0. In this case, epsilon 2 equivalent must be greater than or equal to the critical value of epsilon 2 C naught, where epsilon 1 naught is given by x t by E 1, epsilon 1 C naught is given by x c by E 1. These are the fiber tensile and compressive strains, and epsilon 2 naught is equal to y t by E 2 and epsilon 2 C naught is equal to y c by E 2 are the matrix tensile and compressive strains. X t, x c, y t, y c are the strength values in tension and in compression in the respective directions. Epsilon 12 naught is S 12 by 2 G 12, epsilon 13 naught is S 13 by 2 G 13, and epsilon 23 naught is defined as S 23 by 2 G 23 are the shear strain strength values. Yeah. Now, the next, moving on, we have seen how we can define a damage model. Next we move on, we will see how we can use plasticity based failure criteria for defining damage in composite. So, here in next few slides we are going to see a plasticity based failure damage model. So, the composite system consists of an elastic plastic matrix reinforced with the continuous perfectly aligned cylindrical elastic fibers. So, fibers are considered elastic and the matrix is considered to be elastic plastic because the matrix would undergo more amount of micro cracking and damage. So, essentially the matrix is considered to be elastic plastic. So, sigma bar m and sigma bar f be matrix and fiber effective stress vectors. So, the effective stress vectors are represented by sigma bar m is equal to sigma bar 1 m, sigma bar 2 m and sigma bar 3 m, and sigma bar f is denoted as sigma 1 bar f, sigma 2 bar f, sigma 3 bar f transpose to denote the two vectors for effective stresses for both fiber and matrix. So, the overall effective stress vector sigma bar is denoted by sigma 1 bar, sigma 2 bar and sigma 3 bar transpose. Now, the elastic stress concentration matrices B bar m and B bar f for matrix and fiber are essentially 3 by 3 constant matrices. So, essentially what is going to happen is there is going to be a stress concentration. So, the stress concentration in matrix and stress concentration in fiber can be of the effective stress can be represented in this fashion. Sigma bar is the effective stress for the whole composite, and from that composite we can write stress concentrations for matrix and fiber in this fashion. So, sigma bar m is equal to B bar m times sigma bar and sigma bar f is equal to B bar f times of sigma bar. And in case of plastic loading or elastic unloading, the above equation can be written in an incremental form. If we are looking at incremental elastic plastic relationship, then we can write d sigma bar m is equal to B bar m p, which is indicating the concentration matrix during the plastic process times d sigma bar, where d sigma bar refers to incremental effective stress. So, sigma bar is the overall effective stress vector, and it has in its components sigma 1 bar, sigma 2 bar and sigma 3 bar. So, B bar MP is a 3 by 3 elastic plastic stress concentration matrix, which is used during the elastic plastic process to relate the incremental effective stress in matrix
to the overall effective stress d sigma bar, overall incremental effective stress d sigma bar through the B bar MP, which is the elastic plastic stress concentration matrix. Now, let us introduce another notation. S bar and S bar M denote the overall matrix deviatoric stress vectors. So, the deviatoric stress vector is obtained by taking the overall effective stress vector and deducting from it the hydrostatic part. So, S bar is sigma bar minus 1 by 3 sigma 1 bar plus sigma 2 bar plus sigma 3 bar. So, when we deduct the hydrostatic part from the overall stress vector, we will effective stress vector, we will get the matrix deviatoric stress vectors, and we can simplify and write the matrix deviatoric stress vectors as overall S bar is equal to A times sigma bar, and at a matrix level we can write S bar M is equal to A times sigma bar M, where A is a matrix of constants which is given by this particular expression. Now, the overall and matrix backstress vectors are assumed identical to the corresponding stress vectors. So, matrix backstress beta bar M is equal to beta bar, and which is obtained by B bar M, where B bar M is the concentration factor, and this indicates the backstress vector for the overall stress state. In an incremental fashion during an elastic plastic process, when there is a hardening behavior, we are going to have this backstress vector, and we will have d beta bar M is equal to B bar MP times d beta bar. The deviatoric backstress vectors can be written as q bar is equal to A times of beta bar, and we can write q bar M is equal to A times beta bar of M. So, we can write the overall and the matrix backstress vectors in this particular fashion. When there is a kinematic hardening, we are going to have the backstress, and the backstress can be written in terms of beta bar, and it can write for an incremental elastic plastic relation in terms of the concentration matrix, we can write as d beta bar M is equal to B bar MP d beta bar, and same can be written in the case of deviatoric backstress vector. Now, the effective deviatoric stress in matrix now will read S bar M is equal to A times B bar M times sigma bar, where B A times, because we have in the previous expression S bar M is equal to A times sigma bar M. So, we can rewrite in terms of S bar M, we can write as A times B bar M times sigma bar, and on substituting equation 16 into 17, we obtain the deviatoric effective backstress. So, the deviatoric effective backstress will now become, we can write in terms of q bar M is equal to A times B bar M times B bar. By substituting in terms of backstress, we can write A times B bar M times of B bar, the deviatoric effective backstress. So, for a von Mises type of failure criteria, together with the kinematic hardening, the effective yield function will be written like this. So, we have the effective stress is the deviatoric stress minus the back stress. So, S bar M minus Q bar M transpose times S bar M minus Q bar M is your 3 by 2 times of the effective stress square minus the critical value, which is sigma bar naught m square, must be equal to 0, which indicates an onset of failure criteria f bar m, where sigma naught bar m is the yield strength of the matrix material, and the overall composite system can now be written in terms of the effective stress, and in terms of the back stress, and in terms of the in terms of the concentration matrix B bar m. We can rewrite equation 20 as equation 21. Now, the yield function partial derivative vectors can be derived, and one can compute what is the value of dou f bar m by dou sigma bar m for the matrix. Now, let us consider that epsilon bar m and epsilon bar f are the effective strain vectors for matrix and fiber respectively. So, the components of effective strain vectors for matrix are denoted as epsilon bar m is epsilon 1 bar m, epsilon 2 bar m and epsilon 3 bar m, and for fiber we can write epsilon bar 1 f, epsilon 2 bar f and epsilon 3 bar f. The overall composite system, the effective strain vector, can be written as epsilon bar, and then we can write epsilon bar is epsilon 1 bar, epsilon 2 bar and epsilon 3 bar. Just like we had the stress concentration matrices Bm, we can write the strain concentration matrices C bar m and C bar f for matrix and fibers respectively. So, epsilon bar m e for can be written as C bar m times epsilon bar e, and epsilon bar f is equal to C bar f times epsilon bar. Now, let us consider that we can have during elastic plastic process, we can have the elastic plastic concentration matrix C bar MP, which can relate the incremental strain, effective strain in the matrix to overall effective strain. So, d epsilon bar m p is equal to C bar m p times d epsilon bar p during the plastic loading process or during the elastic unloading process. We can write in an incremental fashion as given in equation 26. Now, for the fiber, the total effective strain vector F is used because the fibers are undergoing only elastic deformation. There is no plastic deformation in the fiber. The elastic plastic deformation is happening only in the matrix. So, the elastic and plastic parts of the effective strain vectors in the matrix can be decomposed. So, the overall effective strain can be decomposed into incremental overall effective strain is equal to incremental elastic strain plus the incremental plastic strain, and this can be rewritten for the matrix because the elastic plastic is defined for the matrix. So, one can define an associative flow rule for undamaged matrix material, and the flow rule will give us the direction of the plastic strain increment in the matrix in terms of a scalar multiplier d lambda m. So, one can write d epsilon bar m p is equal to d lambda bar m times dou f bar m by dou sigma bar m, which is defined for the matrix. Now, we know that dou f bar by dou sigma bar is equal to b bar m transpose dou f bar m by dou sigma bar m, and d epsilon bar m p is equal to d is epsilon bar m p d epsilon bar p. Substituting these equations in above equation, one can write d epsilon bar p is equal to d lambda bar into dou f bar by dou sigma bar, where the multiplier d lambda bar is the multiplier matrix which is given by d lambda bar m times C bar m p inverse times B bar m inverse transpose, where B bar m is the concentration matrix because of the stresses. C bar MP is the concentration matrix because of the elastic plastic concentration matrix due to the strain field, or the to define the incremental plastic strain field. So, equation 29 that we have is a non-associative type of flow rule because of the presence of d lambda bar, which has got these two magnification or factors C bar MP and B bar M. Now, one can define an elastic matrix relation d sigma bar is equal to E bar M d epsilon bar, where E bar M is the effective elastic matrix for the matrix material, and the elastic stress strain relationship can now be replaced by using the strain decomposition. We can write d sigma bar M is equal to E bar M times d epsilon bar M minus d lambda bar M into dou f bar M by dou sigma bar M using the flow rule. Now, d lambda bar M can be determined by using the consistency condition. So, the consistency condition for the overall elastic plastic process, that the stress state lies always on the yield surface. So, df bar M must be equal to 0. This means that dou f bar M by dou sigma bar M times d sigma bar M plus dou f bar M by dou q bar M times dq bar M is equal to 0. So, essentially the first term comes because of the stress state in the matrix, the second term comes because of the hardening behavior and because of the back stress, because of the kinematic hardening behavior, where q is the q bar is M is the back stress. So, essentially dou f bar M by dou sigma bar M transpose times d sigma bar M plus dou f bar M by dou q bar M transpose times dq bar M must be equal to 0. So, substituting these two equations and simplifying, we get d lambda bar M is equal to 1 by q bar M dou f bar M by dou sigma bar M transpose E bar M times d epsilon bar M. So, from here one can calculate what is the value of the scalar quantity q bar M, which is in terms of constant material parameter B and an identity matrix I, which is 3 by 3 identity matrix, and is valid for a 1 Mises type of a criteria. So, the effective elastic plastic stiffness matrix can be derived when we substitute the consistency, the equation 34 that we have derived for the plastic multiplier into the stress strain relationships, and d sigma bar M is equal to d bar M times d epsilon bar M. So, from here one can derive what is the value of the elastic plastic stiffness matrix d epsilon bar M, which is defined in equation 37. Now, the effective constitutive relation for matrix has now been evolved. Fiber is an elastic material. In all this process, it is assumed to be elastic. So, the elastic constitutive relation for fiber in an incremental fashion is given by d sigma bar F is equal to E bar F d epsilon bar F, where E bar F is the effective elasticity matrix for the fiber material, and d epsilon bar F consists of entirely of elastic strains. So, the overall constitutive relationship for the composite system is given by d sigma bar is equal to E times d epsilon bar E, where E is the effective overall elasticity matrix for the composite system. Now, we can write the effective incremental overall and local stresses as follows. So, we can split into two parts. So, the stress state d sigma bar is equal to C bar M d sigma bar M plus C bar F d sigma bar F, where C bar m and C bar f are the volume fractions of the matrix and fiber faces respectively, and this decomposition depends on what is the amount of volume fraction of fibers and what is the amount of volume fraction of matrix that is present in the composite. So, by substituting equation 40 back into equations 36 to 39, which define the incremental stress strain relationships for the matrix and for the fiber, we can, and for the overall composite system, we can get what is the value of E bar in terms of volume fractions. We get C bar m, E bar m times the C bar, capital C bar m, plus C bar f, E bar f times capital C bar f. So, in the, to derive the effective overall elastic plastic constitutive relationship for the composite system, the scalar multiplier for matrix d lambda bar is required in terms of the effective overall quantities, and we use the consistency condition one more time to define this scalar multiplier d lambda bar. Now, using the scalar multiplier for matrix d lambda bar, we can define and using the consistency condition, we can define what is d lambda bar that is required for the overall composite system, right. So, scalar multiplier for d lambda bar m can be defined using the effective overall quantities in terms of E bar and d epsilon bar. So, from this expression we can get what is the value of T bar in terms of quantities such as B bar m, B bar mp, E bar and CMP, and in terms of change in F bar with respect to sigma bar, beta bar and with respect to B bar m. So, from here we can obtain what is the elastic plastic stiffness matrix D bar. So, the elastic plastic stiffness matrix D bar is equal to E bar minus E bar times CMP inverse times B bar m inverse times dou F bar by dou sigma bar T bar transpose times E bar. So, equation that is given in 45, d sigma bar is equal to d bar d epsilon bar represents effective elastic plastic constitutive relation for the overall composite system. So, now moving forward, so here we have presented a plasticity based model. So, starting with an effective overall stress definition in terms of concentration and in terms of magnification factors, we have related the stress state, overall effective stress state in terms of sigma bar and sigma f, the overall effective stress vector in terms of elastic stress concentration matrix B bar m, and for an elastic plastic loading in the matrix, we have written incremental stress using the elastic stress concentration matrix, and we have considered the fiber to be elastic. We have defined the deviatoric matrix deviatoric stress vector. Then we have considered definition of a back stress in terms of the magnification or concentration factor, and we have expressed the deviatoric back stress in terms of the deviatoric effective back stress, and we have considered a von Mises type of failure criteria with kinematic hardening, where the reduced stress or effective stress is deviatoric stress minus back stress, and when it is reaching a is like the 1 Mises criteria. When it is reaching a critical value of yield of the matrix material, there is onset of failure. And we have derived a non-associative type of flow rule considering the concentration factors for the matrix and in the strain field for matrix as well as in the fiber. We have derived an elastic plastic concentration matrix for the matrix, and then we have used an incremental strain approach where we have decomposed the strain into elastic and the plastic part in the matrix, but for the fiber it is only elastic. We start with an effective associated flow rule for undamaged matrix, but upon onset of damage or plastic deformation, once the failure criteria is satisfied, because of the concentration factors in both strain field as well as in the stress field, it appears like d lambda bar is representing a non-associative type of flow rule, and we define the incremental stress strain relationship using the flow rule, and we are using consistency condition to get the plastic multiplier in the matrix. Using the plastic multiplier in the matrix and defining an elastic stress state in the fiber, one can define effective matrix elastic plastic stiffness matrix. And for overall composite system, because the fiber is elastic, we can come up with plastic multiplier for the overall composite system to define what is d lambda in terms of d lambda bar m, to define scalar multiplier d lambda bar in terms of overall quantities, considering also the elastic properties of the fiber. So, that will allow us to define the effective elastic plastic constitutive relationship for the overall composite. So, that completes the plasticity based model for the composites. Now, coming to how to represent damage in a composite system, one can do a linear transformation between the stress vector sigma and the effective stress vector sigma bar through a linear transformation matrix M, and this linear transformation M is a 3 by 3 matrix of damage variables phi 1, phi 2 and phi 3, where phi 1, phi 2 and phi 3 can represent different modes of damage, and phi 1, phi 2 and phi 3 can vary from 0 to 1, 0 representing no damage and value of 1 indicating fully damaged state. So, for phi critical can be defined as a scalar parameter to define a characterized rupture, which can be written as under root phi 1 square plus phi 2 square plus phi 3 square. So, the matrix M, which is a linear transformation, can be written in terms of phi 1, phi 2 and phi 3 as 1 by 1 minus phi 1 0 0 0, 1 by 1 minus phi 2 0 and 0 0 1 by 1 minus phi 3. Now, the derivative of the matrix M is calculated using the chain rule. So, when we are looking at dm, the total derivative is equal to dou m by dou phi 1 times d phi 1, dou m by dou phi 2 times d phi 2, dou m by dou phi 3 times d phi 3. So, the dm is denoted as d phi 1 by 1 minus phi 1 whole square 0 0 0, d phi 2 by 1 minus phi 2 whole square 0 0 0, d phi 3 by 1 minus phi 3 whole square. So, the derivative of sigma bar is given by d sigma bar is equal to d sigma 1 by 1 minus phi 1 plus sigma 1 times d phi 1 by 1 minus phi 1 whole square, d sigma 2 by 1 minus phi 2 plus sigma 2 times d phi 2 by 1 minus phi 2 whole square, d sigma 3 by 1 minus phi 3 plus sigma 3 times d phi 3 by 1 minus phi 3 whole square. Now, using dm, we can obtain the relationship between dm and d phi. So, dm times sigma can be written as k sigma times d phi, where k sigma is essentially sigma 1 by 1 minus phi 1 whole square, sigma 2 by 1 minus phi 2 whole square, and sigma 3 by 1 minus phi 3 whole square. Similarly, dm can also operate on beta. So, dm times beta is equal to k beta times d phi, where k beta is beta 1 by 1 minus phi 1 whole square, beta 2 by 1 minus phi 2 whole square 0 0, and 0 0 beta 3 by 1 minus phi 3 whole square, where d phi is denoted by phi 1, phi 2, phi 3, and beta is beta 1, beta 2, and beta 3. So, the effective overall deviatoric stress vector is given in terms of S bar is equal to A times m times sigma, and the yield function for damaged composite material can be written as F is equal to sigma minus beta transpose times H times sigma minus beta minus sigma naught bar m square, where beta is the back stress, H is the a 3 by 3 matrix, which is denoted as m transpose b bar m transpose times A times b bar m times m, where A is a matrix which is defined in terms of the constants that are present, which we have seen earlier in terms of defining the back stress. So, the back stress can be defined in terms of this constant A. So, we have beta bar. So, we can have S bar is equal to A times sigma bar. So, this matrix of constants is helping us to define this matrix A, which is obtaining from the definition of the deviatoric stress, and which is also used in the definition of the deviatoric backstress vectors. So, so that is the vector A or matrix A that we have, which is defined in terms of the constants that are coming from the definition of the deviatoric stress and the backstress. So, we can define M in this fashion. B bar M are the concentration matrix, and M is the scalar damage matrix that we have defined, matrix of damage variables, which we have defined earlier, and using these we can define the matrix H, and dou F by dou sigma will now become 3 times H sigma minus of beta. So, beta and Q are used for denoting the back stress. Here we have used beta to denote the back stress. So, sigma minus beta is essentially indicating the effective stress or the reduced stress. So, and dou F by dou sigma can be written as m transpose dou F bar by dou sigma bar. Now, using these, one can define the scalar damage function. To define the evolution of damage can be defined by defining a scalar damage function as half sigma bar transpose n times sigma bar, where n is scalar overall damage parameter and sigma bar is the overall effective stress, and phi naught square is like the constant value of damage, and L of phi is a function which is used to define in terms of the damage parameter, such that dou G by dou L will become equal to 1, and dou G by dou sigma is defined as m transpose n m times of sigma. So, the scalar damage function is essentially indicated by a phi, which is the overall damage parameter, and n is given by in terms of constant damage parameter 1 dd d1 d dd1, where the value of d is ranging from minus 0.5 to 1, and this scalar damage function allows us to define how the damage is evolving. Now, to determine the evolution of damage vector phi, the dissipation function is used. So, the dissipation function is given by the plastic work that we have, sigma transpose d epsilon p, the work that is done due to damage, sigma transpose d phi minus L times of d phi. We must, and this allows us to define now the problem of damage evolution reduces to the problem of minimization of pi, subjected to the constraint that the state should always be on the yield surface, and the evolution damage evolution function g, the scalar damage function g should go to 0. So, xi is equal to pi minus d lambda 1 times f minus d lambda 2 dot g, where d lambda 1 and d lambda 2 are the scalar Lagrange multipliers. So, by using these two conditions, that dou psi by dou sigma must be equal to 0 and dou psi by dou L must be equal to 0, because dou g by dou L is equal to minus 1, we get d phi is equal to d lambda 2 times dou g by dou sigma, and d phi is equal to minus d lambda 2 times dou g by dou L, and we can define d capital phi is equal to d lambda 2 and d phi is equal to d phi times dou g by dou sigma when we substitute for d capital phi as d lambda 2. So, then we get d phi is equivalent to d capital phi times dou g by dou sigma. So, this allows us to define how the evolution of damage is taking place, and the scalar damage multiplier d phi can be determined by using the consistency condition and substituting the value of d phi and simplifying. We will get d phi is equal to 1 by r dou g by dou sigma transpose times d sigma, where r is any scalar quantity which is denoted by dl by d phi minus dou g by dou phi times dou g by dou sigma. So, equation 71 is now substituted back into the evolution equation for the damage vector phi, and then we get d phi is equal to 1 by r dou g by dou sigma times dou g by dou sigma transpose times d sigma. So, that allows us to define how the evolution of damage is taking place. So, starting with the scalar damage representation in terms of phi 1, phi 2 and phi 3, the effective stress vector is now transformed by a linear transformation using the overall stress vector as sigma bar is equal to m times sigma, where m is written in terms of the scalar damage fields phi 1, phi 2, phi 3. Sigma is in terms of stress state sigma 1, sigma 2, the sigma 3, and phi CR denotes a scalar parameter that is used to represent critical rupture. One can derive what is the derivative matrix dm with respect to phi 1, phi 2 and phi 3. From here we can get what is d sigma bar. So, and once we know d sigma bar and d phi, we can write what is the dm times sigma and dm times beta, where beta is the in terms of back stress. So, we can define in terms of k beta and k sigma, and we can write the effective overall deviatoric stress and the yield function for a damaged composite system in terms of a 1 minus type of criteria, and using this we can define damage evolution through a scalar damage function, and using a minimization approach to defining the evolution of the damage vector by considering that the dissipation is greater than equal to 0, and introducing Lagrange multipliers, we can get pi minus d lambda 1 times f minus d lambda 2 times g, and the two conditions dou psi by dou sigma must go to 0, and dou psi by dou L must go to 0, and the yield should always happen on the yield surface. So, f should be 0 and g must go to 0, will allow us to define the evolution of the damage, and that allows us to define what is the value of evolution equation for damage vector as d phi is equal to 1 by r dou g by dou sigma times dou g by dou sigma transpose times d sigma. So, in summary, we have looked at classification of composites, we have looked at failure theories for composites, and we have looked at a plasticity based approach for how to define onset of plastic deformation in a metal matrix composites. We have seen effective constitutive relationships for composites with damage, and we have seen how stresses in a damaged composite system can be represented, and how evolution of damage can be defined through the means of a potential function, and using Lagrange multipliers and minimization of the potential function, we can get an expression for damage evolution. So, thank you very much for your attention.